There are actually several other types of definitions when we're talking about solutions. And these definitions are just that. They're just definitions. It's how we're defining things when we make a solution. So don't let them confuse you, but there is a lot of math to go along with these. And really and truly it's math that you're somewhat familiar with because it's dimensional analysis stuff. So let's go through the definitions and then we'll look at ways to use those definitions when you're actually approaching problems. So starting from the top, we have something called mass percent. And what this is it's the mass of the solute divided by the mass of the solution. Now, keep in mind that the mass of the solution is made up of the solute and the solvent. So if you have 5 grams solute and 100 grams of solvent, you have to add these two values together to get the total mass of that solution. And then since it's a percent, you multiply by 100. We're going to use those terms kind of a little bit as we move forward because when we address this 100%, we may also remove that 100%, realizing that that number would represent the mass of the solute divided by the mass of the solution. Now, keep in mind that if you have the same units here, say grams is on top and grams is on bottom, those cancel out, which means that mass percent is just given in a percent. So if you're going backwards in a problem, you can just assume that both of those are grams or kilograms or whatever you want to call them. Now, mass percent is useful because instead of taking this times 100%, we can also use this basic definition of mass of solute divided by mass of solution and also talk about how many parts per million or parts per billion you can have in a solution. This is usually used when you have teeny tiny amounts of solute in a given volume of solution. So what we do is we take the mass of the solute divided by the mass of the solvent, just like we did above. And if you're looking for parts per million, you multiply by 1,000,000, which is 10 to the 6th. And if you're looking for parts per billion, you multiply by 10 to the 9th, which is parts per billion. So we don't use the 100% here. That's the only difference, is that we're just using 10 to the 6th or 10 to the 9th. Okay. Next, I'm going to talk about volume percent. And this, just like we have mass percent, we're going to do everything in this case by volume. So this is volume of solute divided by volume of solution. Now I need to warn you all of something. You would think that just like what we did with grams, we could add the grams of solute and the solvent together to get the volume of the solution. But believe it or not, you can add two things together and they will take up less space than what you necessarily think they will. So say that you have 10 milliliters of one solvent or solution, or one solvent, and you add 5 milliliters of a solute. Together, they can come and make 12 milliliters. I know that sounds crazy, but think of it like this. If you have sand and you add water, there's spaces between those sand particles where water can go and stay. And both of them can occupy the same space because one's bigger than the other. And that's exactly what can happen within a solution, especially when you measure by volume. So you have to be careful in this case, okay? Again, if both of these are in liters or milliliters, they will cancel out. So it doesn't matter what unit you're using there, and you do multiply it times 100% because it's a percent. Then we have some mixed things that we don't use as much, but industry uses this for household products more. And that is mass volume percent. Here we have the mass of the solute divided by the volume of the solution. So kind of similar to what we have in molarity. This is going to give the mass of the solute on the top and the total volume of the solution on bottom. Usually, since these do not cancel out, this is given in grams per milliliter, so grams would be on top and milliliters would be on bottom, and then it's multiplied by 100%. Okay. And finally, we have something called molality. Now, unfortunately, this name sounds a lot like molarity, but it is molality. And we're going to use this more probably next semester. But this is defined as moles of solute over kilograms of solvent. And I just want you to be familiar with the fact that that exists at this point in time. I'm not going to make you responsible for using it just yet, but this is something that honestly, that does exist as well, okay? And so let's start looking at some problems. But before I do that, I just want to tell you all, units in this stuff are incredibly important, because if you don't start using your units or you don't use your units reliably, you're going to get yourself confused really fast with these types of problems. Okay, so let's start with the first problem. So here we have a bottle of vinegar, and a common bottle has 5% acetic acid, and it gives you what that formula is. If you assume that this is mass volume, so that's the mass volume percent, what is the molarity of the solution? I actually started us out with a hard problem. So we have to assume that that 5% is mass volume. And if you go back up, you can see that mass volume is usually in grams per milliliter. So if that's the case, we can say that we have 0.05 grams per milliliter. And you may say, why is it that I just said 0.05? Well, remember, we have to take away the percent. So we do that by dividing the 5 by 100. Another way you could have done that is you could have said there's 5 grams for every 100 milliliters. Those are the same numbers. But you have to find a way to remove the percentage, if you will, okay? Next, we have the fact that we know what the structure is, and we can determine the molar mass. Why do I need that? Well, I have a hint here, because molarity is listed. To get to molarity, I have to have moles, right? Because molarity is in moles per liter. So chances are I'm going to need to go this route. And that's why I went ahead and figured that out before I even attempted the problem. If you get all your information, then this becomes an easier problem, because what we're starting with right here is 0.05 grams per milliliter. Well, this is a harder problem also in the fact that we start with something that has units on top and on bottom, and we can only address one of those at a time. If you did these two steps in reverse, that is absolutely okay. I just did it this way because that's what I did. So the first thing that I switched was milliliters to liters. I wanted to switch that out because I need to get to moles per liter. So I'm going to multiply by 1,000 milliliters over 1 liter, and that cancels out the milliliters. And now I'm already in the liters that I want at the end, right? And then the next thing is I've got to get this out of grams and into moles. So grams up top and down below here cancel out, and we end up with a number of moles. So you do the math, and this is what you find out. Now, if you didn't put big M, if you put moles per liter, guess what? Totally the same thing. That's completely fine. So I'm actually going to back up and do an easier problem next. Here we have a 62% volume solution of isopropyl alcohol. We assume that's in water because it doesn't tell you what it is otherwise, but don't worry about it. But that's what's been known to kill COVID-19. If you have a 355 milliliter bottle, how many milliliters are just due to isopropanol? So Here, what we need to do is we need to take this percentage and convert that to a ratio and see how that's volume. Well, you can do that one of two ways. You can either say that there are 0.62 milliliters of isopropanol for 1 milliliter of solution, or you can say, which I have done down here, that there's 62 milliliters of isopropanol for every 100 milliliters of solution. As long as that ratio is the same, you should be fine in this calculation. So then we just multiply 355 milliliters by 100 milliliters of solution. These cancel out. If you want to write solution here to keep it more clear, please feel free to do that. So you should end up in milliliters of isopropanol. And this is what I mean by you got to be really careful as to how much of your units you talk about, okay? So in the next example, we have a soap solution that contains 15 grams of soap and 150 grams of water. So the question is, what is the mass percent of soap in the solution? The key thing here you need to know is that the mass of the solution is solute plus solvent. So keep in mind that mass percent is the mass of the solute divided by the mass of the solution. SOLN is a solution, sorry. So that's what we're trying to find, and that's what we're putting in right here. Okay, times 100% to get the percent, right? So it should be 15 grams divided by, not 150, but both the 150 and the 15 added together, because together that's what makes the solution. Right? And so when you do that, you should get about 9.1. Now I put this thing in MM. And you may have noticed that before I did VV. And you may see that on some products that you have out there. VV means volume. MM means mass over mass. And there's this other thing that says MV. That's the mixed one. That's mass volume. Okay, good. I think I have 2 examples left here. The next one states the bleach is about 5.25% NaOCl by mass. If the density is 1.06 grams per milliliter, how many grams of bleach are in a gallon container? And it tells you that a gallon is 3.79 liters. So these are the 3 data points that we have. If we say by mass, what that's saying is mass percent. So I can take this 5.25 and convert it again in one of 2 ways. I could say 5.25 grams of bleach is over 100 grams of solution. If instead you wanted to say 0.0525 grams of bleach is in 1 gram of solution, that's fine. It's the same ratio. And so whichever one works for you is completely fine. We know that density is given to us up here, and that is 1.06 gram per milliliter. Now the gram is of the solution, not just of bleach, but it's for the entire solution. And we're given the fact that 1 gallon is 3.79 liters. So I'm going to start with the thing that has the least complex units. And that means I'm starting with 1 gallon. What do we need to find here? We need to find how many grams of bleach we have in that 1 gallon. So I'm going to start with 1 gallon and convert that to liters. And I know that I need to convert that to liters because I have milliliters in my density over here, and that's what leads to my grams. So I know I need to have that. So we're going to go from 1 gallon into liters using the conversion. And then I know I need to get it into milliliters because that's going to use my density. So we do that. Here's where we need to be careful. I've got gallons that cancel out, I've got liters that cancel out. I now have milliliters, and I'm going to go into grams. But again, this is grams of the solution, not grams of bleach. Because I'm trying to find grams of bleach, but this will tell you how many grams all of that solution weighs. So I need something to get me out of the grams of everything, the solution, and into bleach. And I do that with the 5.25%. So that's where I get 5.25 grams of bleach over 100 grams of solution. Or you could also use this there if that's what you want to use in exchange. That's fine. In the end, when you do all your calculations, these will also cancel out. You should end up with grams of bleach. Using proper sig figs, you should get 200 grams of bleach. Why? Because you only have one significant figure in the 1 gallon. Okay, final problem. If water from a local lake has 0.005 grams of AU, which is gold, per liter of water, what is that in parts per million or parts per billion? So remember that how we approach parts per million and parts per billion is that we need to figure out how many grams of solute we have for grams of solution. Now, since we have such a tiny amount of gold in our solution, the solution we can assume to be mainly water, like way more water than anything else, which means that we can assume that the density of water is really going to lead to how many grams of solution we have. So let's say we have 0.005 grams per liter, because that's what you are given in the problem, right? Well, switch the liters for milliliters, and we can use the density of water to cancel that out and give us grams of water. Again, the only reason why we can do this is because we have a tiny, tiny amount of that. So if we were to add that to the mass of the entire liter of water, it would be insignificant. And that's the reason why we don't have to worry about it. So we do this, and so for parts per million, we multiply it times 10 to the 6th. And if you do that math, you should end up with 8 parts per million. Doing the same thing, but in the end, multiplying times 10 to the 9th will give you the appropriate parts per billion. So as I said, I know these problems are challenging, but I know that you can do them. So try to do these again on your own and see if you can go ahead and do that. Y'all are doing great. Hang in there.